Okay, so now that we finished with vector calculus and vector analysis, we are going to now move on to the nitty-gritty, and we're going to start by looking at electrostatics, which is the study of electric forces which act on stationary charges. So Coulomb, back in 1781, was the first to demonstrate this experimentally using a torsion balance, and what he showed was that the electric force between two stationary charged particles is inversely proportional to the square of the distance between the particles and is directed along that line which joins the two particles. It's directly proportional to the product of the two charges, and also that for unlike charges they're attracted, and it's repulsive for like charges. So let's just write down this equation for Coulomb's law, which gives us electric force between the two charged particles. And let's first consider our coordinate system. So here we have x, y, and z. Now we're going to consider some charged particle which is located a distance r away, or r prime. Okay, and this is going to be little q. Now remember, r prime is for our source point. And we're going to look at the electric force created by this on some charge, which is given by big Q, which is located at R. Okay, so that's our point of observation. Now, as you saw in the chapter in the lessons on vector analysis, what we have between the two here is our separation vector, which is given by R minus R prime. And what we can write for this is a unit vector. So we have a unit vector which is given by R minus R prime over R minus R prime. Okay, so that's over the magnitude. So let's write down the electric force. So we have F is equal to some constant, which is 1 over 4 pi epsilon naught. It's given by the product of the two charges, so it's given by little q multiplied by big Q over the distance between the two. So this is going to be the magnitude, so it's R minus R prime to be squared by the unit vector. Okay, which gives us the direction. Okay, so there we have it. There's Coulomb's law and the electric force. Now, let's suppose that it's not just one charge that we have, but that we have multiple charges. Okay, so this little one here is going to be given by Q1. We have another one here, which is given by Q2, and that's going to be located at some point or 2 prime. We have another charge here, which is given by Q3. Okay, so if we have a collection of charges and we want to find the force, the electric force is experienced by this big Q, we just use the principle of superposition, and we just add up all the forces, all the contributions from the individual test charges. So what we will have is F will be equal to, again we have this constant here, okay. And inside here we're going to have the force due to the first charge, so we've got Q1 by big Q over the square of the distance between them, just minus R, and we're going to call this R prime 1 to be squared, and we have the unit vector, which is R minus R prime 1 over the magnitude 1. Okay, that's the first charge. Then we have to look at the contribution from the second charge, which is going to be plus Q2 by big Q over the distance between Q2 and big Q. So we have R minus R prime. I'm going to call this R prime 2 to be squared. We write out the unit vector. Okay, plus, and so on. Okay. So here we just add up the contribution due to each of those small test charges. And what we can do then is we can see that we've got Q in each of these, so we can bring the Q to the outside, and we can write now our electric force in terms of Q times the electric field. Okay, so the electric field is going to be the force per unit charge. Okay, so now we've got an expression here for the electric field, which we can write out. Okay, so how does that look? So now we can write our electric field, which depends on position. Okay, so it depends on our point of observation. It changes in space. It can be equal to, again, our constant, 1 over 4 pi epsilon naught. And it's going to be equal to the sum of each of those charges, okay, the contribution due to each of those charges. So we've got the sum of I is equal to 1 for the first charge up to whatever number of charges by Qi over the square of the distance. So I'm going to call this R prime I to be squared, and we've got the unit vector, which is going to be R minus R prime I with magnitude. Okay, so this is our electric field. You can see the electric field is a vector, and it's dependent on position. It's dependent on our point of observation. Okay, so it's dependent on R. Okay, which is a point of observation. We can also, if we were to plot out the field line, suppose we have some positive charge here. Okay, let's say this is a plus Q. We're going to have the electric field is going to be pointing away from it. We have some negative Q. The field lines are going to be pointing into it. And here we can see that we also have a dipole configuration. So the electric field lines are now pointing from a positive Q to the negative Q.